Okay, half-life should be the time taken, all right, for half of the atoms or the initial amount to decay. After the time given of half-life, the remaining balance will be half from the initial amount. To detect half-life, there are 4 ways we'll look at. All right. Number one, we use the mass of the radioactive radioisotopes. Initial mass, let's say 200 grams. After the first half-life, remaining will be 100 grams. So let's say you're given, let's say cobalt-60. Today it's 200 grams. After 5.3 years, the remaining balance will be only 100 grams. All right. So mass. The number 2 system will be the rate or the count per second, the amount per minute or count. So detectors will show radiation level detected, all right, or count surveyed, they call it. So let's say today you have iodine, all right, certain amount, it was detecting 400 counts per second. The radiation detected, like that. After 8 days, you will see it will drop by half, maybe only 2000 counts per second. Okay. Another way to look at fraction, if today you have an amount of radioactive element, which you say half or 1, after the perfect half-life time, this is symbol, half-life time, the remaining balance will be half from the initial amount. If the initial amount was half, after the half-life time, the remaining balance will be 1/4. So this is how we detect half-life. The formula will be initial amount times 1/2 to the power of n, remaining balance. Okay, balance, initial amount, original amount, 1/2 power n. Okay, next, see what happened. Look at the graph. Okay, how to understand the graph of a radioactive decay system. If you have a half-life graph, it's always a curve like this, and then it will never intercept the time axis x. So let's say, for example, initial amount found to be 8,000 count per minute of iodine 131. After the first 8 days, because half-life of iodine 131 is 8 days, you'll see the balance amount recorded will be only 4,000 activity or count per minute. After another 8 days, see, another 8 days will be half of the initial of 4,000 become 2,000. And another 8 days, 2,000 drop to 100. So this is how the graph will be. So every time iodine 131 decay, you get a graph like this. All right. Not only iodine 131, any radioactive element decay, right? Activity or mass or fraction. All right. You get a curve like this. It's always a curve. Always a curve. All right. And this is time. Always remember, this line should not intercept because it will be a fraction because atom, right? So final atom will be there. So this half-life idea. Okay, to count the value of, all right, half-life of a given substance, all right, see what happens. The given substance shows an initial activity of 960 per minute, which dropped to 120 per minute. From 960, drop to 120. But it won't drop immediately. It will go through a decay series. So from 960, drop to 480. 480 will drop to 240 because it will go through half of the initial amount. 480 half, 240. 240 half, 120. So 3 times 1, 2, 3 times half-life has taken place. 3 half-life took a massive time of 168 seconds or total time. So each half-life is 56 seconds. This is how we calculate, all right? Okay, next see. If I want to use formula, okay, now we use the formula to calculate, okay? What is the formula? What you should do? This is the formula given. The remaining balance should be equal to 1/2 to the power of n times the initial amount. So remaining balance is given 120 activity per minute or count per minute. Initial amount was 960 count or activity per minute. and 2 over n. N represents the number of time half-life occurred. So if I follow 120 equals to 1 over 2 n times 960, I bring the 2 over n up, 120 goes down. So 960 divided 120 is 8. So 2 to the power of n is equals to 8. So 2 to the power of n equals to 2 to the power of 3 actually. 8 is equals to 2 to the power of 3. So n is actually 3. So number of time half-life occurred is 3 times. 3 times. So each half-life is actually 56 seconds. All right. So this is by using formula. Earlier we did by using this manual calculation. Okay, let's see. Okay, next one. Number 2. Right. 800 count per second. What will be the number of activation after 16 days if half-life is 8 days? Now let's can directly do us here. 800 count per second. After the first half-life of 8 days, remaining balance will be 400 count per second. 16 days got 2 half-life. Each half-life is 8 days. So another half-life. Right? First half-life, 8 days. Another half-life, another 8 days. Total 16. The remaining balance now will be 200 count per second. So what will be the number of activation of the sample after 16 days? Then 200 count per second. So after 16 days is the remaining balance. Now, number 3. Phosphorus 32 has a half-life of 15 days. How long will it take for 75% of its substance to decay? Now, they're using the percentage idea. So listen carefully. Half-life is 15 days. So initial amount, I take 100%. All right. So after the first half-life, it will decay. Remaining balance will be 50%. So how much has gone? So how long it takes to decay? So first part 50% decay. Okay, next. This 50% remaining balance will decay again. Remaining balance is 25% from the initial amount. So how many percent gone? Another 25%. So what happened? 75% decayed. Right? Because if you take 100, you minus 75, then you get your 25. Betul kan? So what happened? If 75% decay, it took 2 half-life. Each half-life is 15 days. So total time taken should be 2 half-life. 2 times 15, it's 30 days. This is how we calculate. All right? So half-life is 30 days. Total time taken is 30 days. All right? Okay, next. Let's do number 4. Half-life of substance A is 10 days. What is the percentage of substance from the initial quantity have decayed after 30 days? Have decayed, all right? What is the balance left? Okay. So if initial amount is 100%, after the first decay, remaining balance 50. So 10 days gone. 10 days gone. Another decay, remaining balance 25%. Another 10 days gone. 20 days gone. Another decay. First series, second series, third series. Remaining balance is now 12.5%. So total amount gone is 30 days. All right. 30 days is the total time. All right. So now you have to give 2. What is the percentage of substance from the initial amount half decayed? So half decayed will be 100 minus 12.5. 100 minus 12.5, which will be 87.5%. So amount that has decayed is 87.5%. So remaining balance berapa? Is 12.5%. This is how we do, right? Let's try number 5. Okay, substance. All right. So half-life of 20 minutes. What is the fraction left after 1 hour? In 1 hour, got how many half-life? 3. All right. 20, 20, 20, 60 minutes, 3. So first I take the fraction as 1. After the first half-life, remaining balance is half. Another half-life, 1/4. Another half-life, half of 1/4 is 1/8. So what is the fraction of amount left? 1/8. 20 minutes, 20 minutes, 20 minutes, 60 minutes, 1 hour. So what is the fraction left? Left is 1/8 fraction from the initial amount. All right. Let's do question 6 now. So activation 1/4 from initial amount. That means balance remaining is 1/4. So before that, it should have been 1/2. Before that, it should have been 1. So 1 will undergo decay, form half. Half form 1/4. So first half-life, second half-life. So half-life occurred twice, 2 times. Right? So what is the age of the bone? So total time. So the n times the number of time times half-life. So number of time occurred twice. Total time, half-life time is 5730. 5730 years. So what is the total time taken? 5730 times 2. You get 11,460 years. So if you realize the whole bone is 11,460 years old. This system shows that initial amount after the first half-life, remaining balance half, another half-life. So after the first 5,730 years, the balance half. Another 5,730 years, the balance 1/4. So let's say remaining is 1/4. So 2 half-life took place, the bone is 11,460 years old, right? Okay, this is the basic formula to calculate the energy produced during fusion. So E equals to mc square will be used to identify amount of energy produced whenever there's a nuclear fusion or fission or decay. So this is a fusion reaction. So simplify, we have hydrogen 2 and hydrogen 3 fused together to form helium and releases 1 neutron and energy. From where this energy came and what is the amount of energy released? So we want to calculate that. So what we do, to use this formula equals to mc square, you have to find the total mass before. Hydrogen 2, hydrogen, total mass before is this plus this. So when you plus, you get total mass this plus this, 2.01410 plus 3.0165, you get this. This is the total mass before. The unit is an atomic mass unit. It's not kg, it's not gram. Then, the mass after, total mass after is, all right, 4.00260 plus 1.0867. The total mass after the fusion reaction is this. To identify defect mass, what is the defect mass? The differences between before and after. So Einstein says the mass is converted to energy, right? So what is the amount of mass lost during the process? It will be before minus after. We realize the mass is actually 0.01888 in atomic mass unit. How to change the atomic mass unit to kilogram? Always times this value. This value will be given. All right, so take the defect mass in atomic mass unit, 0.01888, times this value, you get the mass in kilogram. All right, you can only use the formula once the mass is converted to kilogram. So it's in kilogram now. So substitute here. C is always speed of light. C is always speed of light. So always use C equivalent to 3 times 10 to the power of 8 meter per second. So you get the value. So you substitute here, so you get the C value here. All right, C, and you get the final answer 2.820672. This is the energy released when one single atom helium is formed, when deuterium and tritium fuse together. Actually, this one happened in the core of the sun. All right. Okay, last question. So what happened? See here, you have uranium-235 bombarded 1 neutron. The product is cesium, rubidium, and 2 neutrons. 2 neutrons here, 2 neutrons, and energy. So I want to know what the amount of energy released. So total mass before is 1 neutron plus uranium-235. You get this value. And total mass after, there's an error, change this. Okay. And 2.92157. So total mass after is this plus this plus this. You get this. So, but these units are in atomic mass unit. Finally, take this minus this, you get this. So defect mass is always before minus after, right? So before minus after, you get this. So what you do, you times this with 1.66 times 10 to the power minus 7 because we're changing the answer to kg. So from the mass in atomic mass unit, you change it to kg, all right? You just times this. Okay, now your answer is in kg. All right. So use the formula equals mc squared, substitute the value in kg, speed of light, get this. So this is the energy released. So amount of energy released, this is the value. All right. Okay. We will continue next week actually.